Probability of disjoint and overlapping events. Example 3. Modeling real life. An archaeologist's lab received 150 artifacts for processing. Of these, 108 are either made of clay or have coloring. There are 81 artifacts made of clay and 34 artifacts that have coloring. What is the probability that a randomly selected artifact is made of clay and has coloring? All right, so the end result is an artifact made of clay and has coloring. So let's start by looking at what we actually have. All right, so we got 150 artifacts. Of those, 108 are made of clay or have coloring. So that's an or statement. We're looking for an and statement right here. All right, there are 81 made of clay, so 81 made of clay, and 34 have coloring. And then we know that 108 are clay or coloring. All right, so what is the probability? We need to figure out what event A and event B are going to be. So let's let event A be made of clay, since that's the first thing we're talking about here. So event A is made of clay. And event B has coloring. All right, so just like in the last example, if these are not overlapping, we can just add A and B together. If it has parts that are overlapping, then that means that we will have to subtract the overlapping part. So let's look at event A. How many artifacts are made of clay? So 81 artifacts are made of clay. All right, so we have 81 out of, we know there's 150 artifacts. And then we're going to add that to event B. So we know there are 34 that have coloring. All right, so if we add these together, we have 81 plus 34. That gives us 115 total. We can see that 108 are either clay or have coloring. So this is the overlapping part here. So we have 81 plus 34, and then we have to subtract the 108. All right, so we just said that these two together were 115. So 115 minus 108. Common denominator stays the same. So 115 minus 108 is 7 over 150. All right, so 7 over 150 will be made of clay and is the key word here, has coloring. So an artifact made of clay and has coloring. So 7 over 150, we can convert that to a percent. It's going to be about 0.047. All right, so that's going to be about 4.7%. So that means that the probability that a randomly selected artifact is both made of clay and has coloring. And that was found using the same formula as before, event A plus event B minus the overlapping part. And we got all of that information from the problem above. Example 4, modeling real life. The American Diabetes Association estimates that 9.4% of people in the United States have diabetes. A medical lab has developed a sample diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What is the probability that the diagnosis is correct? So we're looking for the probability that the diagnosis is correct. All right, so we have different scenarios here. People with diabetes that is accurate, and people with diabetes, or people who do not have diabetes that are inaccurate. So first, let's think about all the people in the U.S. So out of everyone in the U.S., it says that 9.4% have diabetes. All right, so if 9.4% have diabetes, that means the rest do not have diabetes. So we're always thinking about 100%. So let's see, out of 100%, if we subtract 9.4%, that means the rest do not have diabetes. So 90.6%. So 90.6% do not have diabetes. So 90.6% do not, 9.4 do have it. Together that equals 100%. So we're looking at the people who do have diabetes and do not. So we can think of those as complements. Those events are complements. We discussed complements in one of the previous sections. And then for each one of those, we're going to look at whether the results are accurate or not accurate. So let's make a table and kind of organize this information. So we're going to have event A is going to be a person that has diabetes. And then we want to know about the correct diagnosis. So B is going to be the correct diagnosis. So let's start by saying event A. Event A has diabetes. And event B is going to be a correct diagnosis. All right, so let's look at a table, and there's a nice little table already made. So I'm going to just copy that over so that we can see the different events and kind of look at the percentages from there. All right, so I did try to draw this the first time, but then it was going to be very difficult to read. So I'm just going to copy this out of the book. But you can see the whole population of the United States, event A, and the complement of A, which we discussed right here. And then we have each one, so a person with diabetes can have a correct or an incorrect diagnosis. It gives us that the 98% is accurate, which means 2% is incorrect diagnosis. And then the complement was all the people that did not have diabetes. So that was 90.6%. So that's the complement of A. A person does not have diabetes. And then a correct and incorrect diagnosis. And again, it says 95% accurate for people who do not have, which means there's 5% that is incorrect or inaccurate. All right, so now that we have this table, that's going to make it a lot easier to kind of see what we need to do. So it says we need to find the probability that the diagnosis is correct. All right. So let's use the table here. So when it says the probability that a diagnosis is correct, it doesn't matter whether they have diabetes or they do not have diabetes. We just want to know that they're getting a correct diagnosis. So if you go from a person that has diabetes and they get a correct diagnosis, it's going to give us those two numbers. So we're going to have to multiply those two numbers together to get the first part of the equation. But then the complement of that, the person does not have diabetes, is this, and they get a correct diagnosis of this. So those are the numbers that we're going to be looking at. So let's try to set this up. So we're going to say probability of B correct diagnosis, that's what we want, probability of a correct diagnosis equals the probability of A and B plus, in this case, we've got two scenarios. A and B is event A and correct diagnosis, but we also have to do A complement and event B. So we're going to do probability of the complement of A and B as well. So we are going to be using all four of these numbers to do that. So let's get started. All right, so we're going to have probability of A and B. So we're going to have 0.094 times 0.98. That comes from right here. And then we're going to have the probability of a complement, so 0.906. And then that's going to be times the correct diagnosis, 0.95. All right, so what is that going to give us? I'm going to take this P out because then we can just simplify using our calculator. All right, so we're going to have 0.094 times 0.98. So that's going to be 0.092. And I'm going to go ahead and write all of it out, 1, 2, just to keep it a little bit more accurate. And then we've got 0.906 times 95% accurate. And that's going to be 0.8607. And then if we add those two together, that's going to give us about 0.953. So that's about 95.3%. So the probability that a diagnosis is correct, whether it's a person with diabetes or not, we're just looking for a correct diagnosis, is about 95.3%.